Okay, so chapter 9, chapter review. The 9-chapter review. Every one of these questions, you should make sure to try to do them yourself before just seeing the answer. Very important. Question 1. You're given a bunch of matrices. A equals 5, -2. It's a 2 by 1 matrix. B is a 3 by 1 matrix, 1, -1, 2. C is a 2 by 2 matrix, -1, 3, -2, 4. D is another 2 by 2 matrix, -3, 1, 0, -5. E is a 3 by 3 matrix, -1, 2, 1, -2, 1, 0, -3, -1, 4. And F is a 2 by 3 matrix, 1, 2, -3, -1, 4, -2. Now we're going to have 10 questions, or 10 parts to question 1. For each one, it says, find each of the following without using the matrix utility and the GDC, so no calculators. And if it does not exist, say why it does not exist. So the first one is 2C plus 3D. Well, C and D are both 2 by 2 matrices, so this should exist. 2 times -1, 3, -2, 4, plus 3 times -3, 1, 0, -5. So we have 3 operations here, 2 times the first matrix, plus 3 times the second matrix. Multiplication first. How do you multiply a scalar times a matrix? You just multiply each one. So -2, 6, -4, 8. Plus, same thing here, -9, 3, 0, -15. And how do you add 2 matrices? You just add them slot by slot. So -11, 9, -4, -7. Part B. Oops. Part B says A minus B. A minus B, when you subtract matrices, they have to be the same order, so does not exist since different orders. It is not correct to say no solution. That is different than does not exist. No solution means it's a perfectly valid problem. There is nothing that I can plug in for the unknown, for the variable that makes it true. That's not what we have here. We just have an undefined operation. You're not allowed to subtract these. C is DF. So D is 2 by 2. F is 2 by 3. So I am allowed to multiply them. -3, 1, 0, -5 times 1, 2, -3, -1, 4, -2. And when you multiply a 2 by 2 by a 2 by 3, you end up with a 2 by 3. So there are 6 numbers that we must calculate. So the first one, first row, first column, -3, -1, that's -4. -6, 4 is -2. And 9, -2 is 7. Next one is 5, -20, and 10. Moving on to part D. It says FE. So F is 2 by 3. E is 3 by 3. So I am allowed to multiply them. 1, 2, -3, -1, 4, -2 times E, which is -1, 2, 1, -2, 1, 0, -3, -1, 4. And when you multiply a 2 by 3 by a 3 by 3, you end up with another 3 by 3. Oh, sorry, 2 by 3. The outside ones are 2 by 3. So we have 6 slots. First row, first column. -1, -4, -5, and 9 is 4. 2, that's 4, and 3 is 7. And then 1 minus 12 is -11. 1 minus 8 is -7 plus 6, -1. -2 plus 4, that's 2, plus another 2 is 4. And -1 minus 8 is -9. E squared. Well, you can only square a matrix if it's itself a square matrix. And this one is, so let's duplicate it. And let's duplicate it again. So how do you square a matrix? Well, unfortunately, it's not diagonal. So you can't just square each part. You got to do the math, unless you want to go ahead and do it by the eigenvector-eigenvalue approach, which is the diagonalizable approach, which is certainly acceptable. But for squaring a matrix, I think it's just easier just to go through it, and just do the math. So we have 1 minus 4 is -3, minus 3, -6, -2 plus 2, -1 is -1, -1 plus 4 is 3, 2 minus 2 is 0, -4 plus 1 is -3, -2, and then 3 plus 6 is 9, 9 minus 12 is -3, -6, -1 is -7, -11, and then -3, and 16 is 13. I'm going through these quickly. There's always a possibility that I'm making a silly mistake somewhere. It does happen, but I hope not. F, C plus D, quantity squared. So C and D are the same size, so I can add them, and I get a square matrix, which I can then square. So I'm allowed to do this. C is, well, I have the book here. C is -1, 3, -2, 4, plus D, which is -3, 1, 0, -5. And I want to take that quantity and square it. -1 plus -3, -4, 3 plus 1 is 4, -2 plus 0, and 4 plus -5, which I then want to square. How do I square a matrix? Well, I just multiply it by itself. And you get the same size. So what do I get? 16 minus 8, -16 and -4, 8 and 2, and -8 and 1. So I'm pretty sure I get that. And then we have G. G says evaluate E, B, plus B. Well, E is 3 by 3, and B is 3 by 1. So I get a 3 by 1 matrix, which I can then add to another 3 by 1 matrix. So I'm allowed to do this. So let's go ahead and do it. E is again -1, 2, 1, -2, 1, 0, -3, -1, 4. Multiplied by B, which is 1, -1, 2. And I'm going to add that to B, which is 1, -1, 2. When I do the first multiplication, -1, -2 is -3, -3 plus 2 is -1, -2 and -1 is -3, -3 plus 1 is -2, -2 plus 8 is 6, which I'm then going to add to 1, -1, 2, -1 plus 1 is 0, -4, and 8. So that should be G. H, we're looking for C inverse. That is the inverse of -1, 3, -2, 4. Well, you can always inverse a square matrix. How do you inverse a 2 by 2? You flop, you switch the main diagonal, you negate the off diagonal, and then you divide by -4 minus -6, which is the same thing as 2. So 4 over 2, -3/2, 1, and -1/2. I is CDA. Okay, well, C is 2 by 2, and D is 2 by 2. So when I do that, I get a 2 by 2. And then A is 2 by 1. So when I do that, I get a 2 by 1. So yes, I am allowed to do it. I don't think I've done CD earlier, so just got to do the math. C is -1, 3, -2, 4. D is -3, 1, 0, -5. And A is 5, -2. Of course, by the associative law, I can do this in any order. I can do the first two, get it, times the third, but I think it'll be easier, slightly, to do the second and third. So, because it's a 2 by 2 by 2 by 1, a little less computation. -3 times 5, -15, -2 makes -17, and then we have 10. So I have 17 plus 30, that's 47, and then 34 plus 40 is 74. I think so. Kind of like that, 47, 74, a little symmetric. And then finally we have J, which is C minus 2I2. C is 2 by 2, as is I2. C is -1, 3, -2, 4, minus 2 times the 2 by 2 identity matrix. That's the same thing as -1, 3, -2, 4, minus 2, 0, 0, 2. And -1 minus 2 is -3, 3 minus 0, -2 minus 0, 4 minus 2, and there we go. So that was just the basics of addition, subtraction, multiplication, and taking inverses of a 2 by 2. So now let's move on to question number 2. It says determine the values of A and B such that 3A, 2, -1, 2B, plus 4 times -1, -2B, 1, -A over 2 is equal to 8, 6, 3, -9. So they give us this information. They say, hey, what's A and B? Well, because we have matrix equality, the matrix on the left, and what I mean by the left is the complete matrix on the left, when it's simplified into 1, is equal to the one on the right. So each slot on the left has to match the slot on the right. So if I go ahead and combine them together, I get 3A minus 4, 2 minus 8B, -1 plus 4, that's just straight up 3. And then I have 2B minus 2A. This has to equal 8, 6, 3, -9. Now, of course, the 3 is already balanced. The bottom left entries, nothing to do there. But if I do the top left, giving me 3A minus 4 equal 8. And the top right, 2 minus 8B is equal to 6. That will allow me to solve for A and B. And then I need to check that 2B minus 2A is equal to -9. Because maybe the first two will give me an answer that doesn't work for the last one, in which case there is no answer to the problem. So this becomes 3A equals 12, and therefore A must be 4. -8B equals 4, so B is -1/2. And now we just check 2 times -1/2 is -1, minus 2 times 4 is 8, does in fact equal -9. And therefore, these two numbers do in fact work, and the problem is complete. Question number 3. It says solve each equation for x, where x is a matrix. 3x minus, this is part A, minus 2, -1, 1, -2 is equal to 3, 5, negative 7, 0. How do you solve for x? Well, you get x by itself. How do we do that? Let's first add that matrix to the other side, just as if it was a variable. So when we add it, we get 5, 4, negative 6, negative 2. And then we divide by the number 3, which you can do. You can't divide by a matrix, but you can divide by a number. And if you don't like dividing, you can say multiply by a third. Either way, we get x is equal to 5/3, 4/3, negative 2, negative 2/3. So that was part A. Part B, we have 1, 3, negative 1, 2 times the matrix x equals the matrix negative 5, 2, 1, negative 10. So here, what do? Well, we have to solve for the matrix x. How are we going to do that? Well, we have to get rid of the matrix on the left. How do we do that? Well, you can't divide by it, but you can multiply by its inverse. Now, which side are we going to multiply by the inverse? Well, you have to multiply on the left. If you put x, the inverse here on the right, on both sides, of course, because whatever you do to the left, you have to do to the right. You don't have the matrix 1, 3, negative 1, 2 times its inverse because they're not next to each other. You got to put it on the left. So 1, 3, negative 1, 2 inverse, whatever that is, times 1, 3, negative 1, 2 times x equals 1, 3, negative 1, 2 inverse times negative 5, 2, 1, negative 10. What is this product of matrices? It's the identity. Anything times its inverse is the identity, and the identity times x just gives me x. So on the left, we just get x, assuming, of course, the inverse exists, which technically I haven't confirmed yet. We'll see on the right whether it exists. What would the inverse be? Well, you switch those, you negate those, and then you divide by the determinant, which is not 0, so it does exist. And 2 minus negative 3, you divide by 5, times negative 5, 2, 1, negative 10. So we get 1/5 of, and now we do the product. So negative 10 and negative 3 is negative 13. 4 and 30 is 34. Negative 5 and 1 is negative 4. 2 minus 10 is negative 8. And that's essentially your answer. You can always, of course, go one step further and factor that 1/5 in, or maybe factor is the wrong word, but distribute that 1/5 in. But mathematically, it's still correct. And then the last one is the matrix x times the matrix 3, negative 1, negative 4, 2, plus 3 times the 2 by 2 identity matrix is equal to 5, 4, 2, 6. So our goal is to get x by itself. What do we do first? Well, let's subtract over the identity matrix. So we have x times 3, negative 1, negative 4, 2 equals 5 minus 3, 4, 2, 6 minus 3. Remember, 3 times the identity has 3's along the main diagonal, but 0's everywhere else. So when we subtract 3's along the main diagonal, you leave off diagonals the same. Now, we want to multiply by the inverse of 3, negative 1, negative 4, 2 to get rid of it, but this time we must do it on the right. Of course, both sides. If you do it on the left, you get the wrong answer. So on the right, what do we get? We get 2, 4, 2, 3 times, what is the inverse? Well, switch those, negate those, and then divide by 6 minus negative 4, divide by 10. So what do I get? I get 4 and 16 is 20. I get 2 and 12 is 14. I get 4 and 12 is 16. I get 2 and 9 is 11 over 10. So 2 7/5, 8/5, 11/10 would be the answer to part C. Okay, question number, oh, that's not straight. Question number 4. Question number 4. It says, write each system as a matrix equation and then solve it using matrix algebra. So the first one, we have 7y equals 4x minus 20 and 3x is equal to 2y plus 10. First, I'm going to write this as negative 4x plus 7y equals negative 20. And 3x minus 2y is equal to 10. So I can write that as negative 4, 7, 3, negative 2 times the unknown xy equals negative 20, 10. And then we're going to solve for the xy by multiplying on the left by the inverse. So negative 4, 7, 3, negative 2 inverse times negative 20, 10. How do we get the inverse? We flip those. We negate those. And then we divide by the determinant, which is 8 minus 21, and multiply that by negative 20, 10. So 40 minus 70 is negative 30, and 60 minus 40 is 20 over 8 minus 21 is what, negative 13. So the answer should be 30 over 13 and 20 over 13, and negative 20 over 13. In other words, because we're solving for x and y, so let's be very explicit, x equals 30 over 13 and y equals negative 20 over 13. And when in doubt, you can always go back and check by plugging them into the original problem and seeing if you get the right answer. I'm working quickly because these videos are long enough. Hopefully they're right. B, w equals 3 plus 2y plus 2z. 3y minus 4z equals 6 minus w. And 4w plus 5y minus 3 is equal to 2z. And so first we're going to rewrite them as w minus 2y minus 2z equals 3. W plus 3y minus 4z equals 6. And 4w plus 5y minus 2z is equal to 3, which becomes 1, negative 2, negative 2, 1, 3, negative 4, 4, 5, negative 2. Acting on w, y, and z in that order gives me 3, 6, 3. And therefore, what is w, y, z? If we multiply on the left by the inverse of this matrix, 1, negative 2, 1, 3, negative 4, 4, 5, negative 2 inverse times 3, 6, 3, we get my answer. How do you do an inverse of a 3 by 3? Well, that's where the calculator comes in handy. So let's edit and put in a 3 by 3 matrix. 1, negative 2, 1, 3, negative 4, 4, 5, negative 2. Let's also go ahead and put in a 3 by 1 matrix of 3, 6, 3. And now we want the first matrix inversed times the second matrix. And I get 0, 0, negative 1.5. Let's check whether that worked or not. If w and y are both 0, in the first one, I get a true statement. In the second one, I get a true statement. And in the third one, I get a true statement. Look at that. Now you'll notice, by the way, hopefully you did the same way I did, that your calculator might have a 0 for the second slot, but that first slot does not look like 0. The first slot says negative 1e negative 13. That is negative 1 times 10 to the negative 13th power, which is negative 0.00000000. I've lost track of how many zeros I said, but essentially you have lots of zeros. So you have to recognize that your calculator is using some sort of an algorithm. And that algorithm that it's using doesn't provide the number 0. It provides negative 1e negative 13, but you have to You have to recognize that that really is just 0. And there's no other way, because we don't know, we haven't learned how to take the inverse of a 3 by 3 matrix without a calculator. I guess what you could do is go back to the inverse and make the inverse into fractions on your calculator. Let's do that. Matrix inverse, and then make it into fractions. And you can actually get some nice fractions there. Here, I'll just show you without actually writing it down, just so you see what I'm talking about. So I had it put into fraction mode, and those are the exact values via fractions, and then you can go ahead and do the math that way. But if you understand what your calculator is giving you, it's a little easier. And C says 6x equals 5y plus 18, and 27 minus 9x equals negative 7.5y. This is the same thing as saying 6x minus 5y is equal to 18. And 9x minus 7.5y is equal to 27. Notice how I brought 9x to the right, but then wrote them in the opposite order. And this gives me 6, negative 5, 9, negative 7.5 times xy is equal to 1827. So that what is xy? Well, if we multiply by the inverse on the left, those switch places, those negate. We divide by 6 times negative 7.5 minus negative 45. Uh-oh, we divide by 0. In other words, this inverse does not exist. Well, if the inverse does not exist, then we have a problem. If your inverse does not exist, then you cannot solve it by multiplying by the inverse. Even though you can write it as a matrix equation, you cannot solve it that way. So let's go back to this version here and see if we can figure out what the problem is. The problem is that if you take the first equation, 6x minus 5y equal 18, and multiply it by the number 1.5, you get the second equation. In other words, these two equations are redundant. Now, in the past, the book has been, oh, that's a typo, let's fix it and change it. But it's not a bad idea to know how to fix it. I mean, you can't fix it. I mean, it is what it is. But the answer is that there's infinitely many solutions, because 6x minus 5y equals 18 is really the only equation we have here. And therefore, the answer is anything that satisfies 6x minus 5y equals 18. I am, however, curious. I'm going to pause for a second and check the typos for this to see whether or not they fixed that. Well, it looks like they have not. So just more typos on their part, or at least I don't think this is what they meant, because I don't think they would ask you a question like that. But nevertheless, the answer to this problem is the collection of xy with the property that 6x minus 5y is equal to 18. This is technically the correct answer, versus the other problems where there was a unique answer. This one has infinitely many solutions. What can you do? Yeah, I wish I can share with you the file of typos. There's thousands of typos. Anyways, question, and they don't even have them all. I find typos that they don't have. So, okay, question 5. Parallelogram PQRS. So you have this parallelogram PQRS. Vertices P is -4, -2. So there's P. Q is -1, +7. So there's Q. PQ. R is 8. 1, 2, 3, 4, 5, 6, 7, 8, and 4. There's R. And then S, T, PQR. Okay, well, there's another one. They say parallelogram PQRS, and they give you the vertices as PQRT. So, wow. So the T is wrong because everywhere else in the problem they use S. So we'll just call it S. 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So there's S. Is that a parallelogram? Yeah, within the limits of my artistic abilities, certainly seems like one. So it says the parallelogram PQRS is translated by the vector -3, 5. And now we know that a translation is adding the vector -3, 5. Then enlarged by a factor of 1/2. And then enlarged by a factor of 1/2. And we know that that, if we remember our formulas or if we had the formula book, means being multiplied by 0.50, 0.5, and then reflected across the x-axis. And what is the reflection across the x-axis? I should have it memorized, but I don't want to make a silly mistake. Reflection across the x-axis is reflecting across the line y equals 0, theta is equal to 0, cosine of 0 is 1, sine of 0 is 0, sine of 0 is still 0, and negative cosine of 0 is 1. So we have these three done left to right. Notice I put commas in between because it's first we do this one, second we do this one, and third we do this one. But when you write it as a matrix problem, remember that the first thing is on the right, then you go further to the left. So A, it says determine a single transformation of the form AX plus B that maps PQRS to its image P prime, Q prime, R prime, S prime. So we want to take this to its image. So as always, you should be trying to do this yourself. Okay, so we'll start with P. P is -4, -2. So here's -4, -2. And then we translate it by -3, 5, giving us this. Then we multiply by this matrix on the left. Then we multiply by this matrix on its left. And what we get out of this is going to be our solution. Now, or at least where P ends up. So what I'm going to do is I'm going to replace P with XY and do it algebraically. And then I can go ahead after the fact and plug in all the 4 coordinates. Rather than doing it one at a time, I'll do it once and then plug in the answers for each one. So first I can multiply these 2 matrices on the left, and I get 0.5, 0, 0, -0.5. And I can add these, giving me x minus 3, y plus 5. And in fact, let's do it a little differently. Let's distribute and write it as times xy plus the same one times -3, 5. So this gives me 0.500 -0.5 times xy plus, and here we have -1.5, and then we have -2.5. Because it says for part A, we want to write it in the form AX plus B. So the matrix A is 0.500 -0.5. The matrix X is your unknown XY. And the matrix B is -1.5, -2.5. With that knowledge under our belt, it says determine the coordinates of P prime, Q prime, R prime, and S prime. So P prime, we take 0.5, 0, 0, negative 0.5, and multiply it by p, which is negative 4, negative 2, and then add negative 1.5, negative 2.5. So this gives us negative 2 and 1 plus negative 1.5, negative 2.5. So we get negative 3.5, negative 1.5. So on my thing, I'm going to go to negative 3.5, negative 1.5. You know, I might have to make another one because it looks like it's having a tough time seeing it, but about there. Well, it made a little red dot in the picture. Hopefully you can see that. That's P prime. All right, now let's do Q prime. So the same 0.50, 0, negative 0.5, this time times Q, which was negative 1.7, plus negative 1.5, negative 2.5. So I have negative 0.5 and negative 3.5, plus negative 1.5, negative 2.5. Negative 0.5 is negative 2, negative 6. So Q prime goes to negative 2, negative 6. So that's Q prime. All right, so there's a first side of our new shape, whatever it is. Then we're going to go to R prime. We do the same 0.50, 0, negative 0.5, this time times 8.4, plus negative 1.5 and negative 2.5. Whoops. And that's equal to 4, 0, 0, negative 2, plus negative 1.5, negative 2.5. That's 2.5, negative 4.5. So 2.5, negative 4.5 is about there. That's my R prime. And then finally, we have S prime, which is 0.5, 0, negative 0.5 times 5, negative 5, plus negative 1.5, negative 2.5. And we get 2.5, 2.5, plus negative 1.5, negative 2.5. And that gives me the 1, 0. And 1, 0's there. Okay, and within the limits of my artistic abilities, not half bad. So then it says for part C, determine the area. Oh, well, we know that the area of P prime, Q prime, R prime, S prime is some constant times the area of P, Q, R, S. And the question is, what is that value of K? What is that constant? Now, I also know that that K is equal to the determinant of the overall transformation, or the absolute value of the determinant of the overall transformation. So let's think about it. When you translate a vector to a new position, the shape is not changing at all. You've merely shifted it. So the area is exactly the same. So we can ignore the translation, the shift, and focus entirely on the other two parts, which was the enlargement by a factor of 1/2 and a reflection across the x-axis. But a reflection across the x-axis also has no effect on the area. So all we really have to focus on is the enlargement by the factor of 1/2, which, if we go back up here, is this matrix right here. That's the only part that matters. The translation has no effect, the reflection has no effect, but the enlargement, of course, does. And what is that determinant? It's 0.5 times 0.5 minus 0, 0.5 squared times minus 0, 0.5 squared, 0.25, and therefore this is equal to 1/4 of the area of the original PQRS. So the constant is equal to 1/4. All right. Question number 6. It says the linear transformation x prime y prime is equal to -3, 1, -1, 4 xy plus -1, 2. So first of all, let me just preface by saying this is not linear. This is an affine transformation because it has the plus part. The linear transformation cannot have a translation. So that's another typo. So the linear transformation maps the points xy to the point x prime y prime. That's what it does. A. Find the coordinates of the image of -3, 5. Okay, no problem. -3, 5. I'll just plug it in. -3, 1, -1, 4, acting on -3, 5 plus -1, 2. So I get 9 plus 5, I get 14. I get 3 plus 20, I get 23 plus -1, 2. This takes me to 1325. Okay, no problem. B. The coordinates of the point whose image is -7, 0. So now we're looking for the point that maps to -7, 0. So the x, y, those are the unknowns at this point. And we're going to solve for them. It's a little more work. Let's first subtract off -1, 2. So -7 minus -1, -7 plus 1, -6, 0 minus 2 is -2, equals -3, 1, -1, 4, acting on xy. We want xy by itself. So we're going to multiply on the left by the inverse of this 2 by 2 matrix. Those switch, those negate. Divide by -12 minus -1, and then multiply by -6, -2. So we get -24 plus 2 is -22. -6 plus 6 is 0 over -12 plus 1 is -11. So we get the very nice numbers 2, 0. So 2, 0 would map to -7, 0. And then C, the coordinates of the image of A to A. So now it's just giving us a generic A to A, and it wants to know where does this A to A end up. So I get -3A plus 2A, that's -A. I get -A plus 8A is 7A plus -1, 2. So it just goes to -A minus 1, 7A plus 2. It's kind of a weird question. Okay. Moving on. So then we go to question number 7. This is the last question for the chapter review. We have a series of triangles, T0, T1, T2, and so on, formed by rotating each triangle anti-clockwise by an angle theta, and also enlarging by a factor of k. They give me a picture here. The first triangle looks something like this. They call that T0. The next one looks something like this. Oh, that's not at all what it looks like. It looks something like, I think that's too much. Oh, maybe not. Okay, so it looks something like this. They call that T1. The next one, something like this. They call that T2. And the next one looks something like this. They call this T3, and so on. So we can see that we're rotating, and we are also, they call it an enlargement factor, but apparently this enlargement factor is less than 1, so it's actually shrinking. A. Given that the series of transformations can be described in the following way, the nth x and the y in the nth y are some matrix times the previous x and the previous y, Determine the 2 by 2 matrix A. What is the 2 by 2 matrix A? Well, on my diagram, which I didn't specify before, so if you didn't have the diagram in the book, it'd be hard to see. This point there is 4, 4. And this point here is 8, 0. And of course, the origin is 0, 0, which makes this triangle, let's see, okay. And at this point here, this is the important part here. This point right there is 0, 2. And this point here is negative 1, 1. Okay. And those are going to be the key. Because if we see that 0, 0 keeps going to 0, 0, as these things rotate, right? As these things rotate counterclockwise, anti-clockwise, 0, 0 is like a pivot point. And this thing is rotating about 0, 0. But what I do notice is as follows. What I notice is if you follow 4, 4, 4, 4 first goes to there, and then it goes to there. 4, 4 will go, it'll rotate and then rotate again. So if I apply a squared to 4, 4, it ends up at negative 1, 1. Similarly, if I apply a squared to 8, 0, if I apply a squared to 8, 0, it ends up at 0, 2. Why does this help me? I'm hoping it helps me, because what I'm noticing is from this, I should be able to determine the enlargement factor. I should be able to determine the enlargement factor because the area of T0 is 1/2 base times height. The base is 8, the height is 4, so the area of T0 is 16. Meanwhile, I don't know the area of T1 because I don't know those coordinates, but I do know the area of T2. T2 is a base of 2. If you look at this side, here's 2, and that's 1. So the area of T2 is equal to 1, which means that the area shrinks by a factor of 16 over the course of 2 transformations, which means your enlargement factor should be, or your area is going to be 1/4, right? So the determinant of A, absolute value at least, should be equal to 1/4. So that when you perform it twice, it becomes 1/16. Now, what exactly is the form of A? A is an anti-clockwise rotation. So A is equal to an anti-clockwise rotation. Well, if I look at my formula book, that's cosine of theta, negative sine theta, sine of theta, cosine of theta. That's the formula for an anti-clockwise rotation, followed by an enlargement factor of K. K, 0, 0, K. Okay, now, I know that the determinant of K, the determinant of A is going to be 1/4. So that means that K has to be 1/2. So that its determinant is 1/4. Now remember, You might say, well, what about the other part, the rotation part? Rotation does not change the area. So the determinant of the rotation matrix has to be 1. It plays no role. And in fact, if you think about it, cosine squared plus sine squared is 1. So k has to be 1/2. Now the question then becomes, what is the angle of rotation? So let's think about it. This angle right here is, if you draw a perpendicular down, then it's a isosceles triangle, which means this is 45 degrees because it's 4 to the right and 4 up, 45 degrees. But this, of course, is 90 degrees because it's straight up the y-axis, which means that the rotation angle is 45 degrees. And what is cosine of 45 degrees? Root 2 over 2. What's sine 45 degrees? Also root 2 over 2. So what we get is root 2 over 4. And then we get negative root 2 over 4. And then we get root 2 over 4. And then we get root 2 over 4 again. Let's just check. Root 2 over 4, root 2 over 4, negative root 2 over 4, root 2 over 4. So that is the matrix A. Now that we have the matrix A, we can answer the second part, which says, what are the exact coordinates of the vertices of T3? In other words, we want to apply the matrix 3 times. So a cubed applied to 0, 0 is, of course, going to be 0, 0. A cubed applied to 4, 4. And they want the exact coordinates. Well, that is annoying, but certainly doable. I mean, I have A, and I can certainly raise A to the 3rd power, but if I use radicals, my calculator will not give me exact coordinates, which means, aha, this is the same thing as A acting on A squared acting on 4, 4, which is the same thing as A acting on negative 1, 1. Because we've already established above that A squared acting on 4, 4 is A is the same thing as negative 1, 1. So we get root 2 over 4, negative root 2 over 4, root 2 over 4, root 2 over 4 acting on negative 1, 1. And that gives me negative root 2 over 2, 0. And finally, what's A cubed acting on a 0? Well, that's the same thing as A acting on 0, 2, which is root 2 over 4, negative root 2 over 4, root 2 over 4, root 2 over 4 acting on 0, 2, which gives me negative root 2 over 2, positive root 2 over 2. And if you look at the picture, T3, X is negative, Y is positive, isosceles triangle, it all works out. Wonderful. Now, notice in that problem, I was looking at it like, oh my God, A cubed? Well, I can't use my calculator. How do I do this? And I realized there has to be a way of doing it. There has to be a trick that will save me a lot of time. And sure enough, there was. Part B. So it says the nth and yx values are some matrix times the initial x and y x values. Part I, write down C sub 1. In other words, x1, y1 is C1, x0, y0. Well, in that case, C1 is nothing more than A. It's my transformation matrix, which was root 2 over 4, negative root 2 over 4, root 2 over 4, root 2 over 4. That's what the matrix is. It's the transformation matrix. then it says find C2. Well, x2, y2 is C2 acting on x0, y0. Then C2 just becomes a squared. Well, what is a squared? A squared is, this one I just got to do the math, root 2 over 4 times negative root 2 over 4. Wow, see, it's funny. All that math that I was really excited about avoiding in the last step, it looks like I have to do it after all. Oh, well. So what do I get here? Oh, so I get 2 over 16, that's 1/8 plus 1/8, that's 1/4. That's the top. Or is it? No, the top is 0 because you get 2 over 16, 1/8 minus 1/8. The next one is minus 1/4. The next one is positive 1/4. And the one beneath that is 0 again. So C2 is just 0, negative 1/4, 1/4, 0, which does make sense because that's a 90-degree rotation with a k factor of 1/2. So 1/2, 1/2, it shrinks by 1/4 and 90 degrees at the same time. What is C3 is therefore a cubed, which is 0, negative 1/4, 1/4, 0 times the original a, root 2 over 4, negative root 2 over 4, root 2 over 4, root 2 over 4, which gives me negative root 2 over 16, negative root 2 over 16, root 2 over 16, and then negative root 2 over 16. And C4 is a to the 4th, which is just a squared. I'm not going to use a cubed because it's got radicals, a squared being sort of diagonal. It's the wrong diagonal, but it's still diagonal in a different sense. I can just do a to the 4th is a squared times a squared. This gives me negative 1 over 16, 0, 0, negative 1 over 16. Okay, and then finally it says part III. This is the last part. It says find the sum of the areas of T0, T1, T2, dot, dot, dot. So the area of T0, we've already established above, was 16. The area of T1 is 1/4 of that, 4. The area of T2 is 1/4 of that. The area of T3 is 1/4 of that, and so on. And we want to find the sum of all the areas. In other words, we want 16 plus 4 plus 1 plus 1/4 forever. So if you've done the chapter on geometric series, or if you've covered geometric series, then I can write this as 16 plus 1/4 of 16 plus 1/4 squared of 16 plus 1/4 cubed of 16, and so on. Now, whether you've done this chapter on geometric series or not, if you recognize this as being a geometric series, because each term is the common ratio of the previous one. In other words, you start with whatever number, you multiply it by something to get the next, multiply it by that same thing to get the next, multiply by that same thing to get the next. So it's 1/4, 1/4, 1/4, 1/4. If you look at your formula guide for this section, here we go, AH11 1.11. What is the sum of an infinite geometric series? It's equal to the first term over 1 minus that common ratio, as long as the absolute value of that ratio is less than 1, which ours is. So I get 16 over 3/4 which is 1664 thirds. So the total area of some is 64 thirds. That takes us to the end of the chapter review. Coming up next, exam style questions. See you there.